The binary array search algorithm works exceptionally well when you have contiguous arrays. But as I've already explained, working with large arrays has its own problems. And what you really want to find a way is to break that up into smaller chunks, because it would be easier to store in memory and ultimately easier to update and remove elements from that collection. So I'm now going to introduce a fundamental concept in computer science called the binary tree data structure. It is necessary for understanding many of the algorithms that we'll be covering, but it's also fundamental to the concept of recursion, which is a key concept in computer science that allows us to store data in recursive form, which means that there are like elements in the structure that we can take advantage of. Here's a binary tree that contains 7 elements. And when you first look at it, it doesn't even look like they're ordered. And yet, it has a very deep structure that we can take advantage of to rapidly search through and find elements, and also to add or remove elements efficiently. As a recursive data structure, we start with the concept that a binary tree is nothing more than a collection of nodes, which is a shorthand for a binary node that exists in a binary tree. Each node has a value, and it has a left or a right child. The topmost node in a binary tree is a special designated node known as the root. And if I were to imagine the structure of a binary tree, I would start by saying that a binary tree is a single node, which is the root. And every binary node has a potential value, which is an integer in this case, but of course it could be any value you might imagine. And it has either a left or a right child. So that's the basic structure. With that binary tree, you can actually now impose a global property known as the binary search tree property. And with this in place, we now have a sophisticated structure that allows us to achieve the performance gains we just saw in binary array search without being limited to a contiguous block of memory. Here, we start with the same binary tree, and that root node 7 has the following property. If you look at all the elements to the left, what I call the designated tree T left, that's a binary tree of 3 elements, with 5 as its root and 2 and 6 as its children. On the right-hand side, there's another binary tree which I call T right, whose root is 10, has children 8 and 12. As you observe the larger structure, you can see that all the values that are contained in the left subtree are smaller than or equal to the root's values, and all the values in the right subtree are greater than or equal to the root's values. This observation is fundamental to understanding how the binary search tree is structured. It gives you the exact same hierarchical structure that we saw in binary array search, but it no longer requires a contiguous block of memory. And so what I'm going to show you now is how you would implement this in Python, and after having done so, to take advantage of the contains or in operator, like we talked about, but then also move on and explain how you can insert and delete and visit all the nodes in the tree, which is fundamental to most algorithms where you're trying to store a collection within which you are going to be inserting, removing, and containing objects. So now let's translate these concepts into Python. And again, as I've mentioned, I find it very useful to start from scratch when explaining concepts, because it helps explain to those just starting out with Python, how do you organize your thoughts and how do you organize your code appropriately. I'm going to be using some object-oriented capabilities of Python, and there are plenty of textbooks and online references that you can find to learn more about these concepts. I will only use the most basic of the object-oriented concepts today. I need to have a binary tree, which is the reason why I've done this. So I will create a class. In Python, the way that the syntax looks takes a little bit of getting used to, but after you've seen it after a while, it starts to make sense. With every object-oriented language, there's a need for a constructor, which allows you to construct object instances of that class. In Python, it's this very strange-looking init method with 2 underscores both before and after. And I'm going to start with the premise that every binary tree has a root, but initially it's empty. I need to define what those nodes will actually be. These are binary nodes. And again, they themselves will have their own init method. And what I want to do is create a binary node. In this case, I'm going to be using integer values to be stored, but you can make it whatever you might want it to be. Every node has a value, could have a value. Every node has a left child. And every node has a right child. And I'll just set my function up to allow me to be able to create binary nodes by passing a value that I'm going to use. When you have a binary tree, your first concept is naturally, I want to add a value to that binary tree. So we will write that function here, which inserts a value into the proper location in the binary tree. When the binary tree is empty, it has no root. So if that's the case, then I can safely say, well, my binary tree is now consists of a single binary node whose value was just passed in. Otherwise, now comes the hard part. Where do I put this value, given that I already have a binary tree with some nodes that are structured? Well, to do that, I ask the root to add the value at its proper location. So now I need to have an add method in the binary node class. And this adds a new node to the tree containing this value. If it turns out that the value that you're trying to add is smaller than the value stored at that node, I now know that that value belongs in the left subtree. Recall the binary search tree property, which states that given a node, all the values that are smaller than or equal to that node are stored in the tree that's rooted on the left-hand side. If the value is greater than the value contained in the node, then it belongs in the tree that's rooted on the right-hand side. And I just have one small little trick to play here. It may be that there is no left subtree. And so in that case, I just have to create it. So if it turns out that I have a left subtree, then I can go ahead and ask it to add the value. But it could be the case that there is no left subtree, and I will create it with this value right away. This is the left-hand side. I need the right-hand analog as well. So it could be the case that the value that I'm adding is greater than the self value, in which case I repeat this logic. If there already is a right subtree rooted at self.right, then I ask it to add the value. Otherwise, it too is a new tree that I can create based on the value. This implementation, as you see here, is a recursive implementation that takes advantage of the recursive nature of the binary search tree. When I put all this together, I now have one last thing to check. Now that I have the capability to create a binary tree and add elements to the binary tree, I naturally need to check whether a certain value is in the binary tree. This gets back to our contains discussion. So let's write a contains method for the binary tree that checks to see if a certain target value is contained there. Binary search tree contains the target value. What I want to do is execute what's called a walk down the binary tree. This is very much like having a telephone phone book, starting in the middle and cutting the problem in half by searching through 400 pages, then 200 pages, then 100 pages, and so on. I start at the root, and I say, well, as long as I have some element to look at, I will do the following sequence of steps. It could be that the value that I'm looking for is in fact the value that's stored right there at the root, in which case I found it. And I can just return true. However, it could also be the case that the value that I'm looking for is smaller than the value that I have there. In which case, I want to go and traverse the left subtree and see if he contains it. Otherwise, I have no choice but to consider looking on the right-hand side. Now, if I ever get to the end of this while loop, then I now know that that value is not contained in the binary tree. And this structure is typical of the way that you can traverse recursive data structures. If you've ever worked with a linked list, you know how you can do a while loop, and at the end of it, you just advance to the next element in the list. This is very similar. I have a binary search tree. I'm starting at the root. As long as I have some node to look at, I return the value if indeed I found it. Otherwise, I advance to start looking in the left-hand side, or I advance to look in the right-hand side. Now that we've implemented the binary search tree, let's check it. And this is a common practice that software engineers do as a matter of habit, which is you write some code, you check it right away. You don't want to go too far without running your code, just in case a defect has crept in when you weren't looking. So I start with running this module, and I will have a new binary tree. And I want to add a value to the binary tree. Let me add 5. Let's see. So now I know that 5 is in the binary tree. But let's check by running the contains function. Let's see if it contains the value 5. And as is common when writing code, defects will arise despite your best intentions. It looks like I've mistyped the name of a value of a field, and in fact I have. Down here, node is a binary node, and it has a value and a left and a right child. Unfortunately, I only called it .val, so I have to make sure that when I inspect the value associated with a node, I use the field name value. Let's try that again. It's my binary tree. Add 5 again. Does it contain 5? False. Boy, I'm surprised. I thought I just added it. So let's go back and look at the code. If I have a binary tree, what is its root? It's a binary node. What's the value? It doesn't look like it has a value. Let's go back and look at my definition. In my init method of binary node, I started off initially by saying, well, I don't know what the value is, and I forgot to actually store it, the one that was passed in. I don't mind demonstrating code with defects because, after all code has defects. You just haven't found them yet. Let's try now. Third time will be the charm. Create a binary tree. Add 5. Does it contain 5? Yes. Maybe it's always returning true. Let's check again. Does it contain 10? That's a false statement. Let's try one smaller. So I've at least demonstrated the ability to add a single element and concerned that it's there. Yes, it is. Let's add a few more. And now, when I check to see if those are contained, they are indeed contained. So I have the rudimentary implementation of a binary tree. It has two classes, the binary tree naturally, and the nodes called binary node. I have the ability to add elements into the binary tree. I have the ability to check to see whether the binary tree contains a certain value. And this is the normal place where you would compare the binary tree implementation with a binary array search implementation. And that's what we're going to do now. You may recall that I had that performance code that would let me check to see whether a certain element was contained in my binary array. I have to do something similar here in my binary tree. So let's call this performance again. And now I want to start by demonstrating the execution performance of the binary tree. We'll start with 1,024 elements. And as long as I have some small number of those, I need to do the following. Well, I need to create a binary tree first, and once I've created the binary tree, then I want to compute the time it takes to perform the contains operation. So to create a binary tree, I'll just start here, and let me just imagine that I'm going to create a random binary tree. I'm going to use that as a starting point because, as we'll see later, if I'm not careful with my binary trees, their performance will suffer if I don't get the structure just right. So to do this, I'm going to create a bunch of random numbers in my binary tree using Python's ability to do so. And so, well, as long as I want to create 1,024 or 2,048 elements, I will add into the binary tree a random number, and I'll just make it between 1 and n, just so I've got something to start with. With this binary tree now that's been randomly created, I want to time how long it takes to find an element. I'll do that here. And we do that by just saying now is the time. And then we actually ask ourselves, well, binary tree, do contains, and I can also use a random number. And then I want to print out the time that it takes to do these. So it'll be n, and then we'll make it now. And then we'll advance to the next iteration. So what this is going to do is create a binary tree starting out with 1,024 elements, and then check for the existence of a random element in that binary tree, and then advance to the next one and grow twice as fast. We've seen this issue in the past, which is when you start working with problem sizes that double in time, I want to make sure that I'm being as efficient as possible. You may see some outliers here. After all, this is a random number that I'm searching for, so I have no way of really knowing which numbers are being generated. But at least I can show in this capability that the binary trees that I'm constructing are able to, at many situations, give you great results because the numbers are in the tree. Other times, they take longer because you have to search the entire traversal from the root to some leaf node. I've at least now been able to demonstrate for you the following. I can create a binary tree, I can add an element to it, and then I can check to see if it contains. Now that we've implemented the binary search tree, we need to discuss some of the issues that arise when using these structures. They're excellent when you don't know in advance how many data items you will have. As you know, with an array, you have to fix in advance the size before you do any processing. And if you have to change or redynamically assign the memory for an array, it takes a lot of time in memory. You also want to use the binary search tree when you have a significant number of insertions and deletions, something that arrays are very poor at doing. So I haven't yet done the removal. I'll get to that in a moment. I've only shown you inserts. But even there, we have to be very careful because it may be the case that our binary search tree becomes out of balance. And the best way to describe that is with an example. If I have a binary search tree with these 7 elements, on the left you see a fully balanced search tree. I know that because as I look at it, I can see that if I'm traversing from the root to any of its leaf nodes, it only takes 1, 2, 3 steps to get to any of those leaf nodes. And as you know, 3 is the magic number. That's logarithm of 8 in base 2. However, if I'm not careful, I could have a binary search tree whose structure looks like this. This is a valid binary search tree structure. As you can observe, every node has a value, and all the elements in the right subtree are greater than or equal to that value. It just so happens that this is skewed heavily to the right, so that there are no left children in this binary search tree. And in fact, this is degenerated into what's called a linked list. And when you consider the performance of searching through a collection, as I showed before, I have to look at all the elements, and that gives me what's known as linear performance. And I'm hoping with the binary search tree to be able to get logarithmic performance. So we have to really consider how the structure of the tree is created. And the one way to deal with that is to consider not just insertions but removals. If I start with this sample binary search tree here, which was grown over time, what if I wanted to remove the value 5? You can't just simply delete it, because after all it would leave the left subtree hanging and not attached anywhere. But we can take advantage of the structure of the binary search tree and observe the following. If you want to remove a node from the binary search tree, if it's a leaf node, that is a node that has no children, the 1, the 3, 8, or 12, then you can just delete it and it won't be in the tree at all. However, it may have children. But what if it only has one child, as you see in this case over here? If I wanted to delete the number 5, well, the trick is to observe that you can delete that value by replacing that entire tree with the subtree that's rooted below it. I'll demonstrate. To delete the number 5 from the tree, I will remove it. But now I have a disconnected tree. And I can take that old left subtree and lift it up to replace the parent node that had been deleted. And in doing so, I now have once again a binary search tree. So those are the two easy cases: when you want to remove a leaf node or remove a node that only has one child. Naturally, however, we have to handle the harder case. What if I want to remove a node that actually has 2 children? It seems I can't, but there's another thing we can take advantage of. Again, reflect on the properties of the binary search tree. I know that all the elements in the left subtree of a node are smaller than that node. In this case, 7 is greater than all the elements in this left subtree. But if you think about this left subtree, it must have some maximal value. And in fact, you can see it here, it's the number 6. So if I could just find the maximum value in the left subtree, then I should be able to replace my node that I'm about to delete with that maximum value. And the reason being, I know that all the elements in the right subtree are already greater than or equal to this node at the root, and therefore they would also be greater than or equal to whatever happened to be the largest element in T left. And at the same time, because I know that that is the maximum element in the left subtree, I know that it's greater than or equal to all the other elements in the left subtree, which means it is a suitable candidate to replace the root node. So if I found it here, I could find that value 6 and then move it up and replace it. So now we're going to show the full implementation of the binary tree with the removal capability added. I'm not going to show you this as it was inserted line by line, because it has some rather complicated logic that you want to make sure you get just right. And you can review this at your leisure after this video. The first thing that we start with is in the binary tree itself. I need to add a method to allow my tree to remove a value. If there is a root, that means there's potentially that value exists, and then I ask a new method called remove from parent. The reason we do this is that I need to have some recursive structure in place that allows me to find where that value exists in the tree. And once I've found it, then I can actually delete it. So the remove from parent logic is very similar to the contains logic, where I start at my node. If it's the value that I'm looking for, then I know that I found it and I can call delete. Otherwise, I go to the left subtree and try to remove it from that, or I go to the right subtree and remove it from that. The real logic is contained in the delete method of the binary tree. And it handles the 3 cases we talked about very simply. If it turns out that the node to be deleted is a leaf, then there's nothing to be done. And I know that I'm a leaf when I have no left or right child. And this function delete returns a binary node, which will be used as the parent in the future. So if this leaf is being deleted, then there's nothing to be returned. I return none. If, however, my binary node here has no left child and only has a right child, then great, I can delete that node itself and replace it with its right child, as you saw on my slides just a moment ago. Alternatively, if it has no right child but only a left child, I can return that, and then that will replace the node in the new tree. This is the logic here that gets a little complicated, but let me remind yourselves what it's trying to do. If I'm trying to delete a node that has 2 children, I want to find the largest value in the left subtree. Well, to do that, it's actually a simple process. I start by looking at my child, which is the left subtree, and I find the largest element all the way to the right, which means I start at that child and I look for his right child. I'm going to call that grandchild. I'm going to continue that process repeatedly going all the way to the right. This will guarantee that I will find the maximum element contained in the binary tree rooted in the left. Once I've found that value, then I have to do a little bit of pointer arithmetic, as we used to call it, to move the values around to make sure that I remove it from the tree and I instead use that as a value to be replaced in the node. And as this code runs, I'll demonstrate it for you. I'll be able to go back to look at the slides and validate this one more time. If I have a binary tree and I add 5 and my 1 and 10, and I know that these values are contained in the binary tree, let me remove the value 5. So now my binary tree no longer contains the value 5. Now 5 had been the root because it had the top one and 1 was the left child and 10 was the right child. And yet this root, now this binary tree that is, still contains the values 1 and 10. And this capability is now demonstrated on just 3 nodes, but because it's recursive, I know it will work for all binary trees. So let's review how to delete a node from a binary tree that has 2 children. The idea is to find the largest element in the left subtree. And I do that, as you just saw in the code, by looking at my child, which was the value 5, and then his right grandchild, which was here. And then I try to progress as many times as I needed to get to the largest element in that subtree. Once I found it, in this case it's 6, I can move it up and then remove it from the left subtree entirely. And as I mentioned, you should review that code after you finish the video to make sure you understand it, because that now finally completes the discussion of what a binary search tree lets you do. It lets you insert elements into the tree. It lets you delete them as you will. And so already it's much more powerful than a binary array search, because there you had no choice but to deal with a contiguous block of memory. And that is very hard to insert and remove from an array. It requires too much time to copy and shift and move elements down. Now when you're implementing binary search tree, you can get quite far, as you've shown here. However, we really need to be concerned with balancing the tree to make sure that when you use it, you always get the maximum efficiency from this. Now the good news is there are several choices available for you that are probably implemented in libraries that you can easily access. They're known as red-black trees and AVL trees. And their implementations, while complex, can be understood, but the more important thing that you need to understand is that you should not be implementing a binary search tree from scratch all the time. These implementations are sound, they exist in code libraries, and you should use them as you can. And what they let you do is work with a binary search tree. It will automatically rebalance the tree as necessary as you insert and delete elements, which will ensure that you get the maximum efficiency out of it, which, as I showed earlier, is that log n behavior that I absolutely need to have. And so when I think about the binary search tree, my efficient choice will be I can use it to both search for containment, insert, and delete, all in order log n time. And this fundamental structure allows you to get great performance enhancements in all the algorithms, many of which you'll be seeing in this course. There's some extra functionality that I will add in the code itself called traversal, where not only do you want to check to see if an element is contained in the binary search tree, you probably want to get them in sorted order, which is something that you could do with a binary array. And once you have this logic in place, then there's no need ever to use a binary array when a binary search tree is available for you. And finally, you need balancing to do the work efficiently. And you shouldn't have to do it yourself. You should use actual code libraries for that purpose. So I encourage you to look at the code after this video, because in there I will add the necessary iteration logic that will allow you to quickly look through and print out all the elements of a binary tree, and then that will close the discussion of the binary search tree.